In this video, we're going to talk about simple gas laws. We're going to talk about relationships between the gas law variables and whether they're directly or inversely proportional. Pressure, volume, moles, and temperature. Same variables as we talked about with the ideal gas law. This is just a summary of the simple gas law formulas that we're going to look at. We're going to look at 4 formulas, actually 5, but the 4th one really is just a combination of 3 of the other ones. We're going to look at Charles's law, which relates volume and temperature, Boyle's law, which relates volume and pressure, Gay-Lussac's law, which relates pressure and temperature, and finally, well, not finally, but Avogadro's law, which relates volume and moles. Finally, the combined gas law is actually just a combination of Charles, Boyle's, and Gay-Lussac. It puts pressure, volume, and temperature into one formula, related exactly the same way. Incidentally, all of the laws except for Boyle's law compare the variables that are directly proportional. Only Boyle's law compares 2 variables, pressure and volume, which are inversely proportional. So what does that mean? Well, most of the simple gas laws, except for the combined gas law, relate 2 variables to each other at a time. That means that the other 2 variables, remember there are a total of 4 variables, the other 2 variables that are not mentioned in the formula or in the law are assumed to be kept constant. That's the only way that the law holds true. So for example, in Charles's law, where volume and temperature are compared, when you change the volume, you change the temperature. The assumption, the implicit assumption there is that pressure and moles of gas are not supposed to change. If you have a scenario where pressure or moles of gas are changing, then you cannot apply Charles's law. Even if you're trying to look at a changing volume and temperature, if you allow moles or pressure to change as well as volume and temperature, then Charles's law will not apply. You must keep the other variables constant. 2 variables can be related to each other either directly or inversely. If they're directly proportional, that means as one variable's value increases, so does the other one. They move together. If they're inversely proportional, as one variable increases in value, the other one decreases in value, and vice versa. They move in opposite directions. Just to recap, the ideal gas law was used for static and unchanging scenarios. Scenarios where you know 3 of the 4 variables and you just need to calculate the 4th, but nothing is actually changing. Everything is remaining static. The simple gas laws are applied to a different sort of scenario. Here, the situation is changing. You have a gas or 2 gases or 3 gases under one set of conditions. Then you vary the conditions and you see how that affects the other variables. So for example, in the case of Boyle's law, which relates pressure and volume, you might have a gas at a particular pressure and a particular volume. If you change the volume, you look at what changes with respect to the pressure. You look at how the pressure changes. So you are not maintaining constant values for the variables that you are comparing. Whereas in the ideal gas law, all the variables were maintained at the same values. You just needed to find out one of the values that was missing. So these are different scenarios, and you can generally tell whether you need to apply the ideal gas law versus the simple gas law, depending on whether things are changing or whether you're simply trying to figure out the unknown variable given 3 constant and known variables. So let's take a look at Charles's law. Charles's law states that the volume and the temperature of a gas are directly proportional. That means if volume let's start with the other way. If temperature is increased, keeping everything else the same, assuming that pressure and the number of moles of gas, meaning the quantity of gas doesn't change, then we should see an increase in the volume. So as you heat something up, the volume of that gas should expand. If you take a balloon and you heat up the gas, the air gas inside of a balloon, if the pressure is to be maintained at a constant and you don't add any more air to the balloon, you should see the balloon expand or swell up into a bigger size. If you keep the volume of the balloon the same, the pressure will build up instead of the volume. So remember, the other variables that are not part of the law must be maintained constant. So pressure and moles are constant in order to be able to apply Charles's law. That's the assumption. It's not stated, so you just have to remember volume and temperature are related directly as long as you keep pressure and moles constant. Otherwise, you cannot predict what's going to happen. This is the mathematical expression, or one way to express Charles's law. Volume 1 over T1. So the 1 here, the 1s represent the before the change, 2 represents after the change. So we might have a certain volume and temperature combination beforehand, and then if we change either the volume or the temperature, we can calculate what happens to the temperature or the volume, respectively, as a result of the change. Another way of seeing this is that the ratio of volume to temperature equals some kind of a constant K. We don't actually have to know what the constant K is. As long as it's equal to a constant, we know that the volume divided by temperature for any gas under any condition is always going to equal the same constant. So if we change the volume, the temperature will change in such a way as to maintain this equality. Well, if that's the case, then we can simply eliminate K and relate volume divided by temperature under one set of scenarios to volume over temperature of another set of scenarios. And we distinguish between these two scenarios by labeling them either 1, V1, T1, or VA, TA, or VX, TX. It doesn't really matter. The subscripts here are simply referring to one set of conditions, the first set of conditions versus the second set of conditions. We could even actually even label these, the volume of carbon dioxide, the temperature of carbon dioxide equals the volume of ammonia versus the temperature of ammonia. From the point of view of ideal gases, remember that the identity of the gases don't even matter. So 1 and 2 can stand for anything we want, and we don't have to use 1 and 2, it's just a convention to separate, to delineate which variables stand for which set of conditions. Charles' law is actually the origin or the study of gases at the time. I know it wasn't called Charles's law at the time when they first began studying these gases, but it's the origin of the absolute scale and the origin of the idea of absolute zero upon which the Kelvin scale is built. The Kelvin scale is an absolute temperature scale. Unlike other scales which set their 0 points at arbitrary points, that don't really mean anything as far as universality go. The Kelvin scales begins at the true 0 of the universe. It is physically impossible to reach 0 Kelvin, and there is definitely no such thing as negative Kelvins. At 0 Kelvin, if it were even physically possible to reach 0 Kelvin, all heat would be removed from any kind of a substance. It would be completely devoid of heat. Labs have actually reached nanokelvins, meaning 10 to the negative 9 units of Kelvin. But it is physically impossible to reach absolute 0 Kelvin, but you can get arbitrarily close. Even the coldest substance, even the depths of space, interstellar space, where you would assume everything is as cold as possible, are down to about a few kelvins, like 2 or 3 kelvins, depending on where you are in space. So even there, you do not reach absolute 0 Kelvin. But in a lab, they've achieved 0.000001 Kelvin temperatures. But these are not at all scalable kinds of temperatures. You'll never own a freezer that can maintain a 0 Kelvin temperature. So it originated with the study of the relationship between volume of a gas and temperature. Notice volume and temperature is Charles's law. Down here below, you can actually see pictured this first part here. They were using the Celsius scale. And so they plotted some points they measured the temperature of a gas and they measured the volume of a gas. And they did that for several points. So they would raise the temperature or lower the temperature of a gas and measure its volume. And then they try again. They say, okay, well, the volume of this gas is X, the temperature of the gas is at this temperature here. And so they would take several samples, they would gather several data points. And what they did was they drew a best fit line, as you always do when you have a lot of data. You graph a plot, either a linear plot, in this case it's linear, or maybe some sort of parabolic or exponential plot. Here it's a linear relationship between volume and temperature. So they drew a line connecting the different points, and then they extrapolated that line. So they couldn't get beyond a certain temperature physically, probably because of the lack of technology. Remember, this was hundreds of years ago. They didn't have electricity or freezers. So after a certain point, they saw where the dots were going. They connected the dots, literally connected the dots. And then all they did was extend the line, extend that graph all the way to the theoretical zero volume. And their reasoning was this: well, if this is where zero volume lays, this must be, we know that it's physically impossible for solid objects to have no volume whatsoever, right? You cannot compress, no matter what, you cannot compress matter into zero space. That would make it infinitely dense. There's no such thing as infinitely dense material. So they reason that, well, once you've reached zero volume, if the gases keep shrinking and shrinking and shrinking, there must be some kind of limit. The limit would be when the gas shrinks to nothing. Once it shrinks to nothing, you can't have negative volume of something, right? You can't have space turning itself inside out. So they reason that must be the absolute limit of volume. Therefore, that must be the absolute limit of how cold it could ever get. And they labeled that zero, the true zero, the absolute zero, meaning you cannot get colder than that point. And they saw that at any pressure, at any temperature, with any kind of gas, all the points led to the same temperature, the zero temperature. Now, since they were measuring in degrees Celsius, they measured at this point, this intersection, this line of theirs, this graph between volume and temperature, intersected the volume, intersected the temperature scale at volume equals zero at exactly not 0 degrees Celsius, but negative 273.15 degrees Celsius. And they relabeled that. Instead of calling it negative 273, they relabeled it and said, well, that must be the true zero. So absolute zero is the true zero. And they relabeled it in honor of Lord Kelvin. They called it the new Kelvin scale. Lord Kelvin was one of the early natural philosophers, what they called scientists back then, who studied natural science, who studied the natural world. His name wasn't even really Kelvin. It was something, I forgot what it was. So they named it in honor of him. So Kelvin, so 0 Kelvin is equivalent to negative 273.15 degrees Celsius. I myself will often even omit the 0.15. I often don't even bother writing it. It has such a small effect on calculations, as I've mentioned before. You can omit it too, don't worry about it. It'll never affect your answers significantly enough to change the answer in any way that would hurt you or that would lead you astray. So that's where it came from. They extrapolated, they graphed the points of volume and temperature and then extended the line beyond what they were physically able to measure until it reached down to the 0 point of volume. And at that point, at 0 volume, the temperature that coincides with that, where the two axes or the two axes sort of intersect, not the axes, but the two variables are sort of set equal to each other, or when one variable is equal to the 0 of the other, I guess that's how I should say it. That was at the negative 273 point. That's why the conversion between Celsius and Kelvin is simply subtracting or adding, as the case may be, 273. Why you don't have to multiply, because it's the same unit. A degree Celsius equals 1 unit of Kelvin. They're the same size units. It's just that the Kelvin starts 273 units further back on the horizontal temperature scale. That's all. That's the only difference. It just starts 273 further to the left on the scale, on the temperature scale compared to Celsius. Okay, so here's just another reminder. Always use the absolute temperature scale, the Kelvin scale, when dealing with gas laws. No gas law should ever have anything but Kelvin temperatures entered into it. Never apply Celsius. And of course, make sure you know how to convert between Kelvin and Celsius. Always add 273 to the Celsius temperature. If you really want to be precise, you can always add 273.15 to the Celsius temperature. That gets you the Kelvin temperature. Okay, let's do an example. I have a red balloon with an initial volume of 125 cubic inches. Now you'll notice with these simple gas laws, you can use any unit you want as long as you're consistent other than temperature. Of course, temperature you should use kelvins, but for anything else, for volume and pressure, you can use any units you want, but you have to be consistent. You have to use them consistently throughout the problem. Don't switch volume units, don't switch pressure units, or you're going to be off by the factor by which you need to convert them. So I have a red balloon with an initial volume of 125 cubic inches. Remember, a cube length is a volume. At room temperature of 25 Celsius. I cool the balloon down to 0 Celsius. What is its volume at the new temperature? So this is Charles's law. So I have volume, I have an initial volume of 125 cubic inches. So I'm going to label that volume 1 equals 125 cubic inches. I have my temperature 1, and that's going to be 25 Celsius. Okay. I have my volume 2. Well, that's what I need to figure out. Volume 2, I need to figure out. And temperature 2 is 0 degrees Celsius. So Charles's law. So if I try to plug this in, I know that Charles's law is V1 over T1 equals V2 over T2. So if I plug in my values, I get 125 cubic inches over 25. Okay. V2 is unknown, divided by our T2, which is 0. V2 divided by 0, that's a problem. Oh, wait, that's okay. I'm just going to multiply it out. So V2 equals 0 times 125. See, I'm not dividing by 0 after all. But wait a minute. I'm going to put 0. 0 volume? Well, that could be a problem because I'm pretty sure my balloon doesn't disappear altogether. What did I do wrong? Let's figure it out. Well, it appears I have inadvertently used the Celsius scale instead of using the Kelvin scale. And these are the kinds of terrible things that can happen. These are the kinds of ridiculous results that you get. Negative volumes, 0 volumes, when you should have actual volumes. So clearly this was all wrong. I did that on purpose. I didn't really forget, in case you're wondering. I just wanted to make a point, and I really want to make that point because it's the most common mistake I see, is to forget that you're supposed to use kelvins. Okay, so let's make sure we don't do this. Let's actually convert now. So 25 is obviously wrong. What we're going to do is we're going to take 25 plus 273, and we're going to get 298 Kelvin for our temperature 1. And our temperature 2 is not going to be 0, but it's going to be 0 plus 273. So our temperature 2 is going to be 273 kelvins. Now we're ready. So now let's do this again. So we plug it in. We have our volume 1 of 125 cubic inches. We have our temperature 1 of 298 kelvins. We have our volume 2, which we're supposed to solve for. So I'll just write V2 here. And then we have our temperature 2 of 273 kelvins. we get V2 by itself on one side by cross multiplying. Or another way you can see this, which is even easier than just cross multiplying, is just recognize that across an equal sign, you can only move things diagonally. You cannot move anything straight across. You have to move diagonally. So I'm going to move the 273 to the upper part of the other side of the V2. So V2 is going to equal 273 divided by 298 kelvins times 125 cubic inches. And so that is going to equal a fraction of 273 divided by 298, which should give us a fraction that is less than 1, and then multiplied by 125, we get 114.5, or I'm just going to round to 115 cubic inches. And cubic inches are just fine for our purposes. Could we have predicted, if not the actual number, could we have at least predicted that the volume of the balloon would have been smaller? Yes, we could have. Remember, volume is directly, and this is the proportional symbol, it's the proportionality symbol is this sort of half infinity symbol right here. Volume is directly proportional to temperature, which means we saw our temperature go down. Therefore, we should expect that our volume should also go down. Did it? Yes, it did. We have 115 cubic inches at the end, cooler temperature, which is less than the 125 cubic inches that we started with. So we saw the balloon's volume go down because the temperature went down. So we could have predicted this result. It's important for you to understand how these work. They work more or less according to your everyday common sense experience. If you heat up a gas, it expands outward. If you cool it down, it shrinks. And you can actually do this for yourself. You can take a container, a very flexible container full of gas, seal it, put it into the freezer, and then watch as the container collapses a little bit. Depending on how flexible the walls of the container are, it might collapse a lot. It might just get crushed. So the gas decreased in volume because the temperature got cooler. So remember, convert your temperature. Do not plug the temperatures in and then convert afterwards. That will not work. As you saw in the first example where I did it wrong, we ended up with 0. Converting that by adding 273, well, first of all, you wouldn't be converting it because you'd have a volume. So you wouldn't try to convert a volume by using the formula for kelvins. So it really doesn't work to convert the temperatures after you've already used them. The damage is already done. Convert the temperatures, each temperature separately before you plug them into the gas laws. I can't stress this is that enough. You're just going to make a mistake otherwise. Okay, let's do another example. Balloons and pistons are the premier examples of Charles's law, mainly because in a balloon and in a piston, which is pictured here, balloons and pistons have movable or flexible walls. They can change their volumes. And that's the reason they're good examples and very typical examples of Charles's law, because Charles's law involves a change in volume. Balloons can expand or contract. Pistons can also expand or contract. They can be moved outward to create more volume, or they can be compressed down, or they can be pushed down. A piston can be pushed down to compress a gas into a smaller volume. Small volume, big volume. So both balloons and pistons allow for a change in volume. That's why they're great Charles law examples. In fact, I'm hard pressed to find any other, sort of real life example other than just throwing numbers at you. That would be good examples for Charles's law. Balloons and pistons. Okay, so a gas inside of a sealed piston. Sealed means what? Sealed means constant moles. If the container is sealed, that means no moles of gas can escape and no moles of gas can be added in. So the word sealed is code for constant N, constant moles of gas. A gas inside a sealed piston initially occupies 650 cc's at 15 degrees Celsius. So this is before the expansion of the gas. This is our beginning 650 cc's, or cubic centimeters, cc. So that's our volume 1, 650 cubic centimeters. At 15 degrees Celsius, so our T1 is going to be 15 degrees Celsius plus 273. That's going to be 288 Kelvin. So I'm going to convert that temperature right away. What must the final temperature be? Okay, so it's asking what must be. So therefore, we don't know what the final temperature is going to be. I'm going to put a question mark for T2, our final temperature. Inside the piston B, in order to maintain the same pressure, so pressure is constant. So we have constant and we have constant pressure. That's good because we need to know that those conditions are not going to change in order to apply Charles's law. With a new volume of 1 liter, 1 liter. How much is 1 liter in cubic centimeters? Remember, 1 liter is 1,000 cubic centimeters equals 1,000 milliliters. Actually, I think I should have said that the other way. Anyway, you know that a liter is 1,000 milliliters, and you know that 1 milliliter equals 1 cubic centimeter. Or if you didn't, you know now, right? So we're going to solve for T2. So we have V1 divided by T1 equals V2 divided by T2. Now be careful here. Since you're solving for T2, you don't want to simply get T2 by itself on one side, but you need T2 to be on top. You need T2 to be on top of the fraction. Otherwise, you're not solving for T2, you're solving for the reciprocal of T2. You don't want to inadvertently solve for 1 over T2. You don't want to do that. So it's important for you to be able to do that. Another way to avoid this is to say, well, maybe I can rewrite my Charles's law equation like this. V2 over V1 equals T2 over T1. Same formula, by the way, just a different rearrangement. Rearrange and then solve for T2. That's another way you can do this. T2 is going to equal T1 times V2 over V1. And so we plug in our numbers. I have T1, which is equal to 288 kelvins, multiplied by our V2, which is 1,000 cubic centimeters, divided by 650 cubic centimeters. By the way, another thing to make sure that you know that you're doing things right, although this isn't a guarantee, is just make sure your units are canceling and you're getting the units you expect. You want your temperature to be in, well, actually, we want our temperature to be in Celsius, but you want a temperature unit at the end of this, at the end of using the formula. So when we plug this in, we're going to take 1,000, which is bigger than 650, divided by 650, and we're going to multiply that by 288, and we get 443 kelvins. But we don't want our temperature in kelvins. So what do? Well, we know to convert from kelvins to Celsius, we're going to take Celsius is equal to Kelvin minus 273, right? Remember, Kelvin equals Celsius plus 273. So if we rearrange this to solve for C, we're going to take C minus 273 minus 273. C is going to equal Kelvin minus 273. So that's going to equal 443 kelvins minus 273 is going to equal 170 degrees Celsius. If I did my math right. And let me just double check myself here. Yeah, 170 degrees Celsius, and that is our answer. Now, realize, just because I gave you degrees Celsius in the problem, just because I asked you for degrees Celsius at the end does not mean you are now free to use Celsius. You are never free to use Celsius. Don't take my using degrees Celsius as some sort of permission or, special dispensation to suddenly switch to Celsius. It's never appropriate to use Celsius in a gas law. That's because the ratio of Celsius and the ratios of Kelvin temperatures are not at all the same. For example, let's take, for example, let me just give you a real quick example of why it doesn't work to use Celsius instead of Kelvin. If you don't need any convincing, then you can go ahead and just skip this part. It'll probably take 3 minutes or so. Let's say you want to compare a ratio of 20 degrees Celsius to 10 degrees Celsius, and you were to divide one over the other. That would give you 2. In other words, 2 times the temperature. But that doesn't really mean anything because 20 degrees Celsius isn't truly twice as hot as 10 degrees Celsius. How do we know? Because let's convert this to the true absolute temperature scale. What's 20 degrees Celsius in kelvins? Well, it's 293 kelvins, and 10 degrees Celsius is 283 kelvins. What's 293 Kelvin divided by 283? This is the absolute scale, meaning we're taking the true ratio measuring heat here. 293 divided by 283 is only 1.03, or approximately 3% more hot. This says twice as hot, or 100% hotter, if you want to measure it that way. But the real value is only about 3% hotter. That's because when you take the absolute temperature scale, these small differences in temperature between 10 and 20 degrees really aren't that big of a deal. It looks like a lot because we've artificially set the 0 for the Celsius scale just 10 units below 10 degrees Celsius, but 10 and 20 degrees Celsius aren't that far apart from each other. They seem further apart only relative to a fake 0 in the Celsius scale. But really the 0 is much further down than these temperatures are really being presented as in the Celsius scale. So that's why taking ratios, and remember, when you're using gas laws, all you're doing is taking ratios of temperatures. Taking ratios of temperatures in Celsius are not meaningful because the 0 is artificially high. It's at a point where that's kind of meaningless. There's still plenty of heat left at 0 degrees Celsius. An ice cube has plenty of heat stored in it. Only at 0 Kelvin have you completely lost all heat in an object. All right, let's move on. I hope that convinces you. Here's another one, Charles's law, where the volume, the second volume, or one of the volumes, is given as a function of the other one. That sounds more complicated than it is, but really what I'm just saying is one is related to the other by some multiple. A helium balloon, always balloons and pistons when it comes to Charles' law, flexible walls of the container, a flexible volume. A helium balloon initially at a temperature of 20 degrees Celsius, so T1 equals 20 plus 273 equals 293 kelvins, is warmed. Okay, it's warming up. So automatically we know if we're going to warm up this balloon, its volume should go up. We know our final volume will be higher. Is warmed up until its volume is 6 times higher. Okay, fine. So volume 2 equals what? 6 times volume 1. What's volume 1? It doesn't really matter. What is the final temperature of the balloon? So T2 is what we're going to find out. Now you may wonder, don't we have it looks like we have 2 unknowns and only one equation, which would technically be impossible to solve, but that's not true. Let's plug it in and find out why this is a completely and totally solvable. In fact, it's a rather simple Charles' law formula. So for example, in fact, I'm going to use the form of this law where I put the volumes on top of each other. So let's say V2 divided by V1 equals T2 over T1. I'm going to use this form of Charles's law. Remember, as long as you know your algebra, you can rearrange Charles's law formula any way you want. And let's plug in our values. V2, well, V2 is equal to 6 times V1. Now let's plug in our V1. We don't have any numbers, so I'm just going to write V1. See what's going on? Then we have T2, which again, I have no idea what T2 is yet because I'm supposed to figure it out. And then T1 is 293 kelvins. Now we simplify. Well, what happens if you have the same variable on the top and the bottom of a fraction? They cancel out, don't they? So the V1s cancel. V1 divided by V1 equals 1. I don't have V1s anymore. I eliminated that variable. So what I have is 6 equal to T2 over 293 kelvins. The 6, by the way, has no unit. So I know now to get my T2 by itself, I know that all I have to do is cross multiply. Remember, when you're moving across an equal sign, you always move diagonally. So T2 is going to equal 293 kelvins multiplied by the unitless 6. Oh, here, sorry about that. Let me make these a little bit more. There we go, Kelvin. So T2 is going to equal 6 times 293. That's going to equal 1,758 kelvins. Remember, it's Kelvin units. Now, of course, we still want our temperature in Celsius. So let's convert. So we take our kelvins, 1,758, let's convert to Celsius. Remember, you don't plug in Celsius, you convert, if you need Celsius, convert your temperature after you're done with the gas laws, convert your temperature to whatever you want it to be. Kelvins minus 273, that's the conversion factor, is to subtract rather than to multiply or divide. And so we get 1,400 and, I'm not sure actually. 1,485 degrees Celsius. Don't worry about the sig figs right now. If you want, you can make this, you can put the right sig figs. It's going to be, well, I don't really want to think about it right now, but don't worry too much about it. We had actually we had only one sig fig as our initial measurement. Everything else from there is going to that ruins everything, gives you only a 1 sig fig answer. Don't give me a 1 sig fig answer, even if it's correct. At least 2 or 3 sig figs. Anyway, 1,485 degrees Celsius is our final answer. So 6 times the volume grows by 6 times, therefore we should expect a much higher temperature because volume and temperature are directly proportional. If volume is increasing by a lot, by a factor of 6, so is the absolute temperature. But notice we didn't end up with 120. We didn't take 6 times 120, 6 times 20 to get 120. No, we took the absolute temperature. Volume is related directly proportional to the absolute temperature, not to some arbitrarily chosen temperature scale. Okay, let's look next at Boyle's law. Boyle's law is the only law where the 2 variables are inversely proportional. As volume decreases, pressure increases. That's the most natural way to say that, because if you squeeze a gas, if you compress a gas, say for example in a balloon, if you grab a balloon and try to squeeze it in your hands, you're going to feel some pushback. If you try to push down on a bicycle tire pump, you're going to feel some pushback as you reduce the volume. The gas inside of the piston or inside of the pump is going to push back against you. That's pressure, that's force exerting itself against the inner surface area of whatever it is you're squeezing. So as you decrease volume, pressure builds up. As you increase volume, you allow more space for the gas molecules, the pressure lightens up, it decreases. So Boyle's law is the only inverse relationship you're going to see. So let's take a bicycle tire pump as an example. This is also another kind of piston, again, because we're dealing with a changing volume, pressure versus volume. This time though, instead of pumping the air out into a tire, let's assume that the pump is actually just sort of blocked. So it doesn't pump air out, thus holding the moles of gas constant. The pump holds up to 800 milliliters of air. So we have our basically a piston here. Initially, we have 800 milliliters of air inside, just gas particles inside of the tube, 800 milliliters. And the pressure is about, and the pressure is about 14 PSI. That's just a little bit under standard air pressure. I push the plunger handle down. So this is very similar, but in reverse to that last example with the other piston. So now all these gas particles are squeezed together. They're fighting each other, squeezed together, trying to fight for space. So now it's at the halfway point, or in other words, 400 milliliters. Or we could have just said halfway, either way. If no gas is allowed to escape, what are we saying there? Constant N. Moles are not allowed to change. That's what we mean when we say no gas is allowed to escape. The moles are kept constant. And the temperature stays the same, so constant N. Again, I'm saying this in order to fulfill the requirements of applying Boyle's law, which relates pressure and volume. Therefore, moles N and temperature T must remain constant. So I'm specifying that in the problem. What is the new pressure in units of atmospheres? So pay attention to units, by the way. So we have P1 V1, this is Boyle's law, equals P2 times V2. I don't think there's any simpler way to say this, by the way. This is probably the easiest it's going to get. So pressure, so our initial pressure was what? Let's make ourselves a little table. That always helps to keep us organized. Pressure 1 was 14 PSI. Pressure 2 was, well, we don't know. We're trying to figure it out. So pressure 2 is our unknown, but we want it in units of atmosphere. So we're going to have to do some converting at the end. We have our volume 1, which is 800 milliliters. Now, even though it says half as much, and I know that half of 800 is 400, I'm going to do something else. I'm just going to write V2 equals 1/2 of V1, or even better, half is the same thing as multiplying something by 0.5, isn't it? Half or 0.5, they mean the same thing. So 1.5 V1, and I'm going to leave it like this, and I'm going to use this in my expression. Let's see if that helps us. So let's plug in now. So P1, 14 PSIs, multiplied by V1, 800 milliliters. In fact, we don't even need to put in the 800. We could have actually just put in V1, but I'll put in the 800 anyway. Well, I'll tell you what, let me do it both ways. Actually, because I just realized that this isn't going to work the way I intended. Okay, so 14 PSI times 800 milliliters equals our pressure 2, which is our unknown. So I'll just leave that as pressure 2, multiplied by, let's first put it in numerically, half of V2, half of our initial value, 400 milliliters, we put in 400 milliliters here. And then we solve. P2 is going to equal 14 times 800 divided by 400 milliliters. So the milliliters cancel out. We get PSIs as our final unit. So that's going to be 800 divided by 400 is 200. That's going to be 28 PSI. And then, of course, we need to convert 28 PSI to, where's the unit? Atmospheres. Convert to atmospheres. We know that every 14.7 psi's is 1 atmosphere. Or at least I hope you remember that. So that's going to be just a little bit under just a little bit under 2 atmospheres. So 28 divided by 14.7, I get 1.90 atmospheres, just under 2 atmospheres of air. The other way we could have done this was we could have said this. We could have said, okay, well, 14 psi, forget about the 800 milliliters. Let's just call it V1. V1, and we say V2 is simply equal to 1/2 V1. So we say P2 multiplied by 0.5 V1. Okay, well, if we have the same variable on both sides of the equal sign, the V1s will cancel out. And what do we end up with? We end up with P2 times 0.5. The V1 disappeared. P2 times 0.5 equals 14. Therefore, P2 equals 14 divided by 0.5, and that's going to equal 28 psi's. So you could have done it that way. You could have completely ignored, and then of course you convert there. You could have completely ignored the numerical values. They were actually superfluous. They were extra. You didn't actually need those values. Once you have a relation, a defined relation between the variable at the beginning and the variable at the end, V1, V2, P1, P2, T1, T2, doesn't matter which variable. If you have a defined relationship between them, then you can put them on both sides of the equal sign according to their relationship, and then just cross them out. They just cancel out, and you're left with just the numerical ratio between the two variables, between the variable before and after. In this case, we had a 2-to-1 ratio of volume before and after. That 2 or 1-to-2 ratio, 2-to-1 or 1-to-2, however you want to say it, whichever direction you're looking at. So we can just use the ratio. We don't even need the numbers themselves, because these are all just ratios. So that's 2 ways you could do it. You can either plug in the numbers literally and solve it, or you can just use the variables ratios, 1-to-half or 2-to-1, same thing. By the way, if I had put a half here, I would have just ended up multiplying the left side by 2, and I would have gotten 2 times 14 instead of 14 divided by half or divided by 0.5. Either way, you end up with 28. And then, of course, you have to convert to atmospheres. Pay attention to units, by the way. That's going to be, it's not intended to be tricky. It just, sometimes you want different units, that's all. Okay, let's try another example. Again, this time completely without numbers, no numbers at all. But we'll see, it doesn't make any difference whether we have numbers or not. So if I triple the pressure of a gas, okay, what does that mean? That means my pressure 2 is equal to 3 times my pressure 1. That's what this means. Triple the pressure of a gas. Well, if my beginning pressure is something P1, then my final pressure is triple that, or 3 times P1. What will happen to its volume, all else being equal? Now, I'm not asking for a specific number. No specific number requested. I'm simply asking what will happen to it. What will happen to the volume? So let's see. So P1 V1 equals P2 V2. What's going to happen? You know what? We don't even need the math here, to tell you the truth, but let's just use it anyway. So we have P1 V1 equals P2 V2. So we know that we know that, okay, where is it? P1 is P1. V1, we don't know yet. P2 is equal to 3 times P1, and then we multiply that by V2. So let's see what we have here. We can see that P1 is going to cancel out on both sides. So what do we have? Well, we have V1 is equal to 3 times V2. What does this mean? Well, what this means is that our V2 is 1/3 of V1. Doesn't that mean that? If we take the 3 and we put it underneath V1, this is what happens. Our final, to read this in words, our final volume, V2, falls to 1/3 its original value. It doesn't matter what its original value was. No specific number was ever requested. All I asked is what will happen? What happens to the volume? The volume shrinks or compresses to 1/3 its original amount. All of these sentences are saying the same thing. I'm just giving you different ways to say it. That's all. Different ways of looking at it. The volume shrinks to 1/3 its original value. It compressed, the gas compressed to 1/3, or it compressed by 2/3. But let's just keep this simple. Let's not say by this. Let's just 1/3 of its original value. And you could have seen this, right? In fact, I'm sure you could have seen this. You know that pressure and volume are opposites. They are inversely proportional. So if I triple the pressure, I get 1/3 the volume. Triple the pressure, 1/3 the volume. If I double the pressure, I get 1/2 the volume. If I quintuple the pressure, I get 1/5 the volume. If I decrease the pressure to 1/2, I double the volume. Whatever you do to one, do the reciprocal, the inverse of the other. And that's the idea behind this. No numbers needed. Another way of saying this is that the ratio of V2 to V1 is exactly 1/3. In other words, the ratio of the final volume to the initial volume is 1/3 of the initial volume. All of these things are just different ways of saying the same thing. Hope that makes sense. Gay-Lussac's law. Gay-Lussac relates pressure and temperature. Pressure and temperature, again, are directly proportional. And this makes everyday common sense, right? If I increase the temperature of a gas without letting the volume increase, in other words, if I heat up a gas, a trapped gas, you can imagine that the pressure is going to keep building up. This is the basis of most bombs. In fact, this is unfortunately, this was the basis of a terrorist bomb in Boston, in the Boston Marathon. They used a pressure cooker. They used pressure cookers. These are home cooking devices to make bombs, because pressure cookers are locked and sealed trapped gases. They put heating devices inside the bombs to build up pressure until the walls of the container of the pressure cookers, these pots, failed suddenly and catastrophically, releasing a whole bunch of pressure at once, killing, I think injuring more than killing, but injuring a lot of people. Some people lost limbs because of this. So you can build up pressure simply by increasing temperature and not letting the gas escape, not having any kind of pressure valve to release pressure. The trapped gas builds up. Again, this also depends on the amount of gas, both sealed containers, so you don't let any gas escape, and rigid walls, so that the container doesn't grow in volume or change in its volume to accommodate the extra pressure and to alleviate the extra pressure. As always, this is one expression, but there are always other ways to express it. You can also put this as P2 over P1 equals T2 over T1. However you want to list this. You can put the P's on one side and the T's on the other, or you can just mix them up. It's all good. It all works. It really is just a matter of what you want. Pressure cooker is the most common example. A sealed, so constant N, and rigid, so constant volume. Sealed always means constant moles because you're not letting any moles of gas in or out. Rigid walls means constant volume because you're not allowing any kind of change in volume. If the walls are rigid, that means they're not flexible. Okay, well, here's a picture of a pressure cooker, although this Yeah, this is actually, it's kind of an old-fashioned looking one. But this is the idea. They even have a pressure gauge on top. I'll be honest with you, this looks more like an autoclave than a pressure cooker. Autoclaves, by the way, in case you've ever been in the medical field, an autoclave is just like a pressure cooker. It superheats gas to over 120 degrees Celsius, 120 degrees Celsius to kill any bacteria in order to sterilize surgical instruments. And it's basically a pressure cooker where instead of cooking food in there, you throw in a bunch of instruments and you sterilize them with heat. They are almost the same device. Okay, so a pressure cooker, which is a pot with a locking lid, it is a sealed, so constant moles, and it has rigid wall. It is sealed and has rigid walls, constant V. So I just repeat that over here. So a pressure cooker is initially at 17 degrees Celsius, so kind of a cool day, and 700 millimeters of mercury. Maybe we're at higher elevation, so local atmospheric pressure is a little lower than the standard sea level. The lid is placed securely on and it's heated to 350 degrees Fahrenheit. What is the pressure in the hot pot? Okay, so let's make our little table here. We're given an initial temperature, T1 equals 17 degrees Celsius. Of course, we need to convert, right? Always, always, always convert. 17 plus 273, 17 plus 273 is 290 kelvins. Pressure one, our starting pressure is 700 millimeters of mercury. Now, there's no reason to convert that unless for some reason since I didn't mention a specific unit, we can go ahead and use millimeters of mercury for our final unit. That's perfectly fine. If I don't specify a unit, then that means it's up to you. If you want to set it to atmospheres, go ahead. So what is the final pressure in the hot pot? So not when it's cool, but when it's hot, heated up. So it's heated to 350 degrees Fahrenheit. Now, of course, we're not going to use 300 Fahrenheit. Who uses Fahrenheit in science? Nobody. So let's convert it to Celsius. So convert to Celsius and then to kelvins. So we have to take it one step at a time. I personally don't like to try and do it all at once. So we know that Celsius equals Fahrenheit temperature minus 32 divided by 1.8. So that's going to be 350 minus 32 divided by 1.8. Be careful, don't say minus 32 divide 1.8. Your calculator will think that you want to divide 32 by 1.8 before subtracting it. Either use the parentheses or hit the equals sign, 350 minus 32, hit the equals button, and then hit the divide button for 1.8. Don't do them back to back without parentheses, or your calculator will think that you want to divide 32 by 1.8. Be careful about that. That's an easy mistake to make. So 350 minus 32, I hit my equals button, I get 318. Then I take the 318 and I divide by 1.8, and I get 177 degrees Celsius. Of course, that's not the temperature I want either, so bear that in mind. 177 degrees Celsius. I want kelvins, so kelvins is going to equal Celsius plus 273. So that's going to equal 177 plus 273. That's going to equal 450 degrees. Is that what it is? 177 plus 273. Yeah, 450. Looks kind of similar to the Fahrenheit temperature. 450 Kelvin, that is our temperature. T2 equals 450 Kelvin. This is the temperature we get to use, not the 350, the 450 Kelvin. And then our P2, of course, is going to be what we try and figure out. We need to figure out what the final temperature is. So we have Gay-Lussac's law. What I'm going to do is I'm going to rewrite Gay-Lussac's law from the original way I showed you. I'm going to write it with P2 on top. This is just algebra, so hopefully your algebra skills are good. For this chapter or this section, you're really going to need some good algebra skills. So P2 divided by P1 equals T2 over T1. You know what? I'm going to double check myself because even I'm not totally sure about my, let's see, P2 over P1 divided T, yeah, equals T2 over, okay, yeah. So just crisscross, move them back and forth, and you get this relationship right here. So I'm going to do this because I want P2 to be on, not only by itself, but also on top. So P2 is going to equal P1 times T2 over T1. That's going to equal, my P1 is 700 millimeters of mercury multiplied by T2, which is 450 kelvins, divided by, let me write that a little bit neater for you, divided by my T1, which is 290 kelvins. So we can already see we're going to have a fraction that's greater than 1. Does that make sense? Yeah, it makes sense because we're raising the temperature. We should expect to multiply the 700 pressure by some fraction greater than 1, which will increase our pressure. Our final pressure should be higher because we've increased the temperature. They're directly proportional. So we take 700 times 450 divided by 290. 450 divided by 290 gets us to about 1.55, and we multiply that by 700, and so we get 1,086 millimeters of mercury. Now, if you wanted this in some other unit, you're more than welcome to convert it. It looks to me to be about 1.3 atmospheres. In fact, let's just for comparison, 1,086 millimeters. I'm going to say about 1.3 atmospheres. Let's see. Every 760 millimeters of mercury, 1 atmosphere, just to have something to come. I just find atmospheres a little bit easier to use to understand than millimeters of mercury, only because it's a lot easier to understand 1 atmosphere than it is to understand some random number like 760. Oh, I was a little off, 1.43 atmospheres. So in case you were curious, it's 1.43 atmospheres. The problem didn't ask for atmospheres, so you're perfectly fine just reporting it in millimeters of mercury. But if it did ask for atmospheres, this is how you convert it. So we raised the temperature. We saw the pressure go up because there was no room for the gases to go anywhere else. They didn't escape, so because moles were kept constant, so there was a sealed pot. And the walls of the container are rigid, so they didn't expand like a balloon or a piston. And you have a little pressure gauge up here. Okay. Another Gay-Lussac example. Now this one again, it's going to be a little bit short on actual numbers because you don't always need numbers. You just need ratios between the variable at the beginning and the same variable at the end, or the variable at the end. So the absolute temperature of a tank holding helium gas, okay, I don't know why I'm underlying everything, holding helium gas is reduced. Okay, the temperature goes down. What should we expect to happen to the pressure? They are directly proportional, therefore pressure should also go down. If temperature is going down, pressure should go down. As you cool the gas inside of a tank, the gas particles move more slowly, they bounce into each other less, they are going to coalesce. They're going to reduce the amount of pressure. They're not going to move as fast, so they're not going to hit the walls of the container as hard or as often. So you reduce pressure. Just keep that picture of a gas in mind. It's reduced to 1/3 of its original value. So temperature decreases to 1/3. In other words, what that means is T2 equals 1/3 of T1. That's what we're saying. The absolute temperature of a tank is reduced to 1/3 its initial value. Well, if its initial value is T1, 1/3 of T1 is equal to T2, the final value. If the tank was originally at 24 PSI, so originally P1 equals 24 PSI, what is the new pressure in PSI? What's P2? You don't even need the math. If they're directly proportional and the temperature falls down to 1/3, the pressure is going to fall down to 1/3. What's 1/3 of 24? 8. 1/3 of 24 equals 8. You don't even need to do the math. However, if you want to do the math, if you want to do this systematically, that of course is perfectly understandable. So let's do that. Let's take T2 divided by T1 equals P2 divided by P1. Okay, well, T2 divided by T1 is the same thing as 1/3 T1 divided by T1. So notice, if you have the same variable on the top and the bottom, those variables cancel out. So you're left with only the fraction 1/3 on the left side of this equation. And then on the other side, we have equals P2, which is 24 PSI, over P1. Oh, I'm sorry, no. What am I saying? Sorry, our P2 is unknown, isn't it? P2 over P1, which is 24 PSI. My apologies. P2 is the unknown. So what do? Well, let's rewrite this. P2 then, therefore, P2 is going to equal 24 times 1/3. Well, what's 1/3 times 24? 8. That's the same thing as saying 24 divided by 3. That's 8 PSI. And since it asks for PSI, we're good. So if two variables are directly proportional, whatever factor you multiply one variable by, you multiply the other variable by exactly the same factor. If it's 1/2 of the original temperature, it's 1/2 of the original pressure. If it's 6 times the original temperature, it's 6 times the pressure. Whatever you do to one variable, you do to the other. When they're inversely proportional, you do the reciprocal to the other, in the case of Boyle's law. But in Gay-Lussac's law, Charles's law, is there another one? Avogadro's law, which we're going to look at soon. You always, whatever you do to one, you do to the other. And once again, you don't even really need necessarily the numbers themselves, although since you've been given a number and you were asked for a specific number, it's more convenient just to plug the 24 in and get the actual number. You could have gotten the ratio of P2 to P1 and then applied it to the 24 separately, but that just breaks up a simple problem into more than one step. And there's no need for that. All right, let's take a look at Avogadro's law. We're going to do something different with Avogadro's law. We're not going to do just the simple plug in this number, figure out that number sort of thing. We're actually going to mainly apply Avogadro's law to stoichiometry. And you already saw in the previous video, if you watched the ideal gas law video, how Avogadro's law can vastly simplify an otherwise sort of complex problem, or at least a multi-step problem. Okay, so you know that Avogadro's law relates the volume of a gas to the moles of a gas. You can either see it in one of two ways. It's actually more often going to be helpful to you in this, expressed in this form, rather than it's the usual form it's expressed in, like, for example, chemistry textbooks and online. Normally, the way it's written online and on textbooks is V1 over N1 equals V2 over N2. Remember, when you see this format, when you see the variables dividing each other, that indicates that they are directly proportional. Notice that Boyle's law was the only one where they were inversely proportional, and you saw the variables multiplying each other. Look at the difference in form. You have V1 over N1, V2 over N2. Look back at Boyle's law. I can go all the way back in any kind of Boyle's law. You notice that the form, where is it? Oh, here it is. Well, I kind of buried the lead here. You see that the form is P times V rather than P divided by V. When the variables are inversely related, you actually multiply them. When they're directly proportional, you divide them out to equal a constant. That's just the way it looks. So you can tell these are, just by looking at the form of the equation, you can tell that these are directly proportional variables. So when I write it this way, A and B can either refer to the same gas, but under different, with a different volume and different number of moles, or it can refer to two different gases. A can be one gas, B can be another gas in the same, involved in a chemical reaction or in a part of a chemical equation. And that's actually, though, the way we're going to use this more frequently. So let's take a look at an example. Avogadro's law applied to stoichiometry. Let's assume we produce sulfur trioxide at the same temperature. Now, of course, this is, again, we're laying the groundwork for being able to apply Avogadro's law. If we don't keep everything at the same temperature and pressure, then we are not allowed to use Avogadro's law. We must keep T and P the same in order to relate N and V together reliably. Given 325 milliliters of each of the reactant gases, so 325 milliliters, 325 milliliters, how many milliliters of sulfur trioxide can we theoretically produce? Notice this is a limiting reactant problem. This is a limiting reactant stoichiometry problem. Limiting reactant, why? Because we've been given specific quantities of both reactants. In other words, it's entirely possible that one of these reactants is going to run out. Now notice we have not been given any grams. We have been given no gram information. We also, again, notice we have not been given any information about pressure or temperature. We've been told that they're at the same temperature and pressure, but we don't have enough information. So here, let's list what we don't have. We don't have grams. So we can't use molecular weight. We don't have a specific pressure and temperature. So we can't use the ideal gas law, PV equals nRT. We can't use this. That's out. Grams per mole, molar mass, that's out. We can't use anything that we would normally use to solve a stoichiometry problem. What are we supposed to do? Avogadro's law to the rescue. In fact, you cannot answer this question in using anything but Avogadro's law. Luckily, Avogadro tells us that the mole ratio of each gas, so for example, let me start with sulfur dioxide. The mole ratio of sulfur dioxide to sulfur trioxide is the same as the volume ratio of sulfur dioxide to sulfur trioxide. And likewise, the mole ratio of oxygen to the moles of sulfur trioxide is exactly the same as the volume of oxygen to the volume of sulfur trioxide. That helps us immensely. What that means is we can now reinterpret these stoichiometric coefficients. We reinterpret them as, well, in this case, we reinterpret them as milliliters, as volume. Avogadro says that as long as what we're comparing are gases and not solids, liquids, or solutions, Avogadro says that as long as all the gases are at the same temperature and pressure, their mole ratios are equal to their volume ratios. Now, don't confuse ratios with absolute amounts. We have no idea what the actual number of moles are because we cannot calculate moles because we don't know we don't know the actual pressure and temperature. So we have no idea how many moles 325 milliliters of sulfur dioxide or oxygen or sulfur trioxide represent. We have volume, but we don't have pressure and temperature. We cannot calculate moles, so we can never know how many moles in an absolute sense. But the ratios are completely equal. We can know that for sure. In fact, we know that the mole ratio of sulfur trioxide to sulfur dioxide is 2 to 2, or 1 to 1, in other words. Therefore, we know that the volume ratio of sulfur trioxide to sulfur dioxide is 1 to 1. In fact, let's take these one at a time. Because this is a limiting reactant problem, we're going to take these one at a time. Just like a regular limiting reactant problem, we're going to calculate the amount of product from each one of our reactants one at a time. First, we're going to do this one, just because it's the first one. And then we're going to do this one second, and whichever one gives us the lower product, that's our answer. That's our limiting reactant, and the result of that, the product that results from the limiting reactant, is our final answer, is our maximum theoretical yield. Okay, so I'm going to have to make a little bit of space here. I'm going to leave the formulas as over here on the right as they are, but I'm just going to delete this part here. It says Avogadro says that as long as all the gases are at the same temperature and pressure, their mole ratios, sorry if this is a little hard to read, their mole ratios are equal to and exactly the same as their volume ratios. That's why I can set these things equal to each other, which is great because that allows us to reinterpret the stoichiometric coefficients in any volume unit we want. So I'm going to interpret this as 2 milliliters of sulfur dioxide reacting with 1 milliliter of oxygen gas to produce 2 milliliters of sulfur trioxide. That's how I'm going to read this now. So what that tells me is that my moles of sulfur dioxide, so I'm going to get my moles from the stoichiometric coefficients. So my 2 fits over here. My 2 over here fits over here. So I have 2 moles of sulfur dioxide to 2 moles of sulfur trioxide equals, so that's a 1-to-1 ratio, equals my volume. Why did I do it this way? I'm sorry. Let me reverse these because there's really no reason to make this harder on myself. I want to solve for SO3. I'm looking for the product. Let me just reverse these. It's the same thing. I'm just flipping the equation around. I did it again. SO3, SO2, SO3, SO2. This allows me just to calculate V straight up without having to worry about flipping the fraction around. So SO3, everything else stays exactly the same. Okay, so my volume ratio here, my volume of sulfur trioxide divided by my volume of sulfur dioxide. But I already know my volume of sulfur dioxide is 325 milliliters. So I solve for VSO3. My volume of sulfur trioxide in milliliters is going to be 325 times 2 over 2, which is just 1. That's going to be 325 milliliters of sulfur trioxide. That's my product from just the sulfur dioxide. I don't know if this is right yet. I have to do the other one. The next one's going to be exactly the same thing. So this is from SO2. Now I'm going to do the same kind of calculation from O2. So we have O2. We know that, again, I don't know why I put these upside down. Let's make life easier, right? NSO3. Let's put the O2 on the bottom so we have this exactly where we want it to be. SO3. It doesn't change anything, right? We're just flipping them around. They're still equal. They're still, everything is, I said, is exactly the same. So we have moles of sulfur trioxide. So that's going to be 2 moles of sulfur trioxide over, now the stoichiometric coefficient here is 1 mole. The chemical equation is telling us what the mole ratio ought to be. It's 2 moles to 1 mole, sulfur trioxide to oxygen. And we set that equal to the volume of sulfur trioxide, which we're trying to figure out from volume of oxygen, to 325 milliliters of oxygen. This was 325 milliliters of sulfur dioxide. So we solve for VSO3. Volume of sulfur trioxide is going to equal 325 milliliters multiplied by 2 over 1. So that's going to be 650 milliliters of sulfur trioxide. So which one is our answer? We had two calculations. One gave us a big number, one gave us a small number. Reject the bigger number. Reject accept the smaller yield. So it turns out that sulfur dioxide was our limiting reactant. So 325 milliliters of sulfur trioxide. How many milliliters of sulfur trioxide can we produce? That's our answer. We reject the big number and we take the small number instead. We couldn't have done this without Avogadro's law. We had absolutely zero information to go from. We had no grams, we had no mass, so we couldn't convert to moles. And we didn't have pressure and temperature, so we couldn't use the ideal gas law to figure out moles either. So we had no other way but Avogadro's law telling us, don't worry, mole ratios, volume ratios, same thing as long as you know pressure and temperature are the same. Let's do another example. This time we're going to do a little bit of a different example, but it's still going to involve stoichiometry. This time we're going to look at total moles. This isn't really anything new. Let's just take a look. 85 liters of methane gas, so we have 85 liters of methane gas, is reacted with 70 liters of steam. Remember, in the gas phase, water is called steam. So we have, again, this is another limiting reactant problem. We know that because we're given specific amounts of both of our reactants. How many liters of product gases? Now, product gases, the implication here is all together, all the product gases will be produced. So let's see how we do this. And by the way, I can ask this kind of question even without invoking Avogadro's law. Any stoichiometry problem could also be worded and phrased this way as well. So again, we're going to use Avogadro's law to figure out how many liters of our product gases we can make. According to the ratio here, and this time I think we already know what's going on. So, but how many liters? What's our liter ratio? What we have here is our mole ratios. Our mole of products, product gases, I should say, well, I'm just going to say products altogether, both CO and 2H2 together. I'm going to count these together. I'm not going to try to separate them. Together, my moles of products, the ratio of my moles of products to my moles of methane equals what? Well, doesn't it equal 1 plus 2? To 1. I'm going to give you a moment to let that sink in. I have 1 mole here. I have 2 moles here. That's 3 moles of products for every 1 mole of methane. Let me color code it. Just because I want to make sure I don't lose anyone while they're watching this video. I'm going to put this 1 here. So I have 1 here. Whoops. Put the green here. I have a 1, remember there's an implied 1 here. This is 2. So I have these 2 together are my product moles, 1 plus 2. So I have a 3-to-1 mole ratio of all my product gases to my methane gas. That's the idea here. That's the only wrinkle here. Everything else is exactly the same. My volume ratio is 3-to-1. So if I have 85 liters of methane, then my volume ratio of 3-to-1 applied to 85 liters, I should have 3 times as many liters of CO and H2 taken together as my methane. So let's work that out systematically just in case. So what this is saying is that for every 85 liters of methane, my ratio of moles is the same thing as my ratio of liters. 1 liter of methane gives me 3 liters of products. That's CO and H2, both of those gases. And so that gets me 3 times 85, which is going to be 255 liters of my product gases, both gases. That's all I'm doing is just adding up the moles. Okay, but do we know if that's our answer? No, we don't know. Actually, it's definitely not our answer, is it? We already can tell. This is a 1-to-1 mole ratio of our reactants. We have fewer we have fewer liters, excuse me. We have fewer liters of water. Clearly, water is the limiting reactant. We have a 1-to-1 ratio. If I have less water, that means water is going to produce less products. But just to convince you, in case you're not totally convinced, let's work it out. So again, for water, it's going to be exactly the same sort of ratio. N products, so our moles of product to moles of H2O is going to equal, again, 1 plus 2 oops. I'm color coding everything here. 2, 1. That's a 3-to-1 ratio again. So we just apply that 3-to-1 ratio. So, but this time we have 70 liters of water. And the ratio here is again 3-to-1, same ratio because they are 1-to-1. After all, methane and water are 1-to-1. So we should expect the same ratio of products to each one of these separately. 3 liters of products to every 1 liter of H2O. And that's going to equal 70 times 3, 210 liters of our product gases. And that's our answer. We reject the other answer because it's bigger, right? We always reject the bigger answer when we take the smaller answer, because in a maximum theoretical yield limiting reactant kind of problem, you always take the smaller amount of product. Whichever reactant generates the smaller amount of product, that's your correct answer. And the reactant that gave you that answer is the limiting reactant. This is the excess reactant. So we can do the same thing. Just like you can involve the ideal gas law in stoichiometry, so you can also use Avogadro's law to simplify your stoichiometry problems. It's really handy. Here's a bad example, and I just want to show you this. We'll just walk through it. There's nothing to work out because this is a non-starter from the very beginning. So this reaction occurs at STP. What is the maximum theoretical yield in moles of calcium oxide given 400 milliliters of oxygen? So we have 400 milliliters of this gas oxygen. We have STP, so we know that 400 milliliters is 0.4, well, excuse me. We have 0.4 liters of oxygen. We know at STP that every 22.4 liters gives us 1 mole of oxygen. That gives us, let's see, where are we? 0.4 divided by 22.4. That gives us a small amount of moles. Then we double that number of moles of calcium oxide. Wait a minute. No, this is a doable problem. What was I thinking here? Given 400 milliliters of oxygen. I think I was thinking of a different problem here. Okay, well, never mind. I'm going to delete this particular. This was not the example I wanted to give you as a bad example. This is actually solvable. What am I talking about? Oh, I think I wasn't supposed to give you the STP information. information. That's what it was. I wasn't supposed to tell you what the standard temperature pressure was. That was supposed to make this an impossible problem to solve. Okay, without STP, we have no idea how to relate the moles and the volumes of the product to the reactant. But I messed that up. So, you know, it was just an example of a bad example. The ultimate point here is this. The only reason I was even going to walk through this is the idea, the whole point of that was supposed to be this. I'm just going to give you the conclusion. Don't apply gas laws. I'm going to write it out instead. Forget the example. Don't apply gas laws to any substance not in the gas phase. At any point. You cannot you cannot apply gas laws to non-gas things. There are going to be times when it looks like you can do that. For example, when we talk about solutions and their concentrations, we're going to talk about the volume of solutions, but that volume is not at all equivalent to the volume of a gas. Anything that is not in the gas phase is completely out of bounds for applying gas laws to. Even if we talk about density and mass per volume, it doesn't matter if we talk about volumes with regards to solids or liquids. Those volumes are not at all amenable to being used and manipulated in gas laws. Gas laws are specifically for gases and not for anything else, not for any other phase other than gases, whether it's solutions, meaning aqueous, or solids or liquids. Only gases can be used in gas laws or can have gas laws applied to them. Don't apply, so don't treat the volume of a solid or a liquid as the same as a volume of a gas. They are completely different and unrelated. That's my point. That was supposed to be the whole point of this. I wasn't supposed to give you the STP. Anyway, it's hard for me to devise a bad example. There's always a way to solve a problem, it seems. There are very few problems that aren't solvable somehow. All right, let's move on. Forget about that. Just remember, don't apply gas laws to anything but gases. That was the upshot of that. Let's do another example of Avogadro's law, but a mixed example, meaning we're going to apply both Avogadro's law and the ideal gas law in this case. Now, this one we really are going to make use out of multiple things, and we can solve it, of course. Okay, at STP, which is the one I'm supposed to give you information about, at STP, remember at STP, that's a kind of a simplifying relationship between moles and volume, liters specifically, and moles of a gas. At STP, carbon, now this is solid carbon, so we cannot do anything regarding carbon and the ideal gas law, but the rest of these are gases, and we can apply the ideal gas law to the gases. Carbon is reacted with 850 liters of hydrogen, so 850 liters of hydrogen to make methane. What is the theoretical yield of methane, first in liters and then in grams? Let's do liters first, A. Okay, in liters. Luckily, the truth is we could actually, we could actually figure this out in multiple ways. We don't even necessarily need Avogadro's law. But you'll see that using Avogadro's law is a lot easier than using the ideal gas. Well, it's easier than using the ideal gas law. For one thing, you can immediately see it's half, or 425 liters. That's your answer to A right away. Why? Because it is a 1-to-2 ratio. The mole ratio of methane to hydrogen, and hydrogen is 1/2, which is going to be the volume ratio, which is going to be our volume of CH4 to 850. So we solve for the volume of methane, and that's going to be equal to 850 divided by 2, or 425 liters. That's our answer. But if you're good at seeing the ratios, spotting the ratios, you can automatically see, 1-to-2, they're both at the same temperature and pressure. Whether it's STP or not doesn't even make any difference. The point is they're at the same temperature and pressure. you can see it's a 1/2, a 1-to-2 ratio, so, or 2-to-1 ratio. So 850 to what is 2-to-1? Well, 850 to 425, half as much. So you can solve this in 2 seconds using Avogadro's law. Now you could use, another way you could have done this was to invoke STP, and you could have said, okay, well, I know that 850 liters of hydrogen, I know that at STP, my liters of hydrogen, let's see, every 22.4 liters of hydrogen gives me 1 mole. I remember that because it's STP. Otherwise, I'd have to plug in all my numbers into the ideal gas equation and figure it out. Okay, so that's 1 mole of hydrogen. Then I know that every 2 moles of hydrogen gives me 1 mole of methane. Okay, great. And then I know that because methane is also at STP, then I know that every 1 mole of methane is also 22.4 liters because they are both at STP, luckily. And so what do I get? Well, you could go through all that and you'd find that, oh, look at that, 22.4 divides out with 22.4. I end up with 850 divided by 2, 425 liters again. But look at all this stuff I had to go through. And what if it weren't at STP? Then you'd have to wait for some other pressure and temperature combination. Then you'd have to use the ideal gas law and you'd have to use it on the hydrogen as well as on your methane, and you'd have to reconvert back again. It'd be just a whole lot more trouble compared to the 2-second, oh, look at my ratio, I'm done sort of activity here. My point is this, that there's more than one way to solve these problems, and some ways are just a lot faster and easier than others if you understand the idea of ratios, mole ratios, and in this case with Avogadro's law and having the same pressure and temperature combinations, pressure and temperature for all the gases, the volume ratios are the same as the mole ratios, and you can treat these stoichiometric coefficients as if they are liters, milliliters, gallons, fluid ounces, whatever volume unit you want, it works. Doesn't work for mass, but it works for volumes of gases. Actually, whoops, not carbon. Carbon's a solid. Never mind, forget I said carbon. Okay, that's the answer to A. Right away, it's 425 liters. You can easily see that by Avogadro's law. Now, we did need the STP information because otherwise we'd have no way, or we needed some kind of information to arrive at a specific number of moles. Otherwise, we wouldn't be able to calculate grams. So now this is harkening back to the ideal gas law. This is more of an ideal gas law problem because the Avogadro's law part of this problem just goes by in the blink of an eye. It goes by so quickly. We're going to spend more of our time just looking at this in terms of the ideal gas law. Well, that's fair. We spent some time on the Avogadro's law and the ideal gas law video. So, okay, so let's do part B now. So how do we figure this out? Well, now that we know that this is 425 liters of methane, that's our yield in volume, 425 liters of methane. We know that every 22.4 liters of methane gives us 1 mole of methane, but only at STP, but luckily we are at STP. So we're good. We can use this relationship. If not, we'd have to use the ideal gas law. We'd have to use PV equals nRT, and we'd have to figure it all out. 1 mole of CH4, but of course we don't want mole, we want moles, we want grams. So that's okay. Every 1 mole of CH4 methane gives us, well, 12 plus 4 times 1 equals 16 grams per mole. So 16 grams of methane for every 1 mole. So that's 16 times 425 divided by 22.4. That gives us 304, if I round up, 304 grams of methane. Now, of course, you don't normally weigh or get the mass of a gas, but in this case, just for the question, we got that. So that's the answer to part B. If for some reason we weren't at STP, what we would have done is we would have simply gone in and calculated N equals P times V divided by RT. We would have plugged in value for pressure, which we would need to have been given in order to solve this. And we would have plugged in a value for temperature, which again, we also would have needed to solve. This would have been 425 liters, nothing's changed there. And of course, the R value is 0.0821. So we'd have to have been given pressure and temperature. We were given pressure and temperature. Remember, STP is a specific temperature and pressure. And then we would have calculated the value of N, and then we would have converted N moles to grams using 16 grams per mole. The rest of it would have looked exactly the same. It wouldn't have been as neat and as sequential as this is, but we would have been able to solve it. So that's an Avogadro's law type problem as well. You don't strictly speaking need Avogadro's law to solve both parts, only because you were given STP. However, I could have omitted STP or any information about temperature and pressure other than to say the temperature and pressure are the same. And of course, that would also mean I can't ask you about part B as well. I can only ask you for A. That would have required you to use Avogadro's law because you'd have no ideal gas law and enough information to use the ideal gas law. So that would have been a possibility as well. And you saw possibilities like that already. Now we come to the combined gas law. Combined gas law really is nothing special. It's just a very quick and easy way to just, if you ever wanted to just forget Charles' law, Boyle's law, and Gay-Lussac's law and say, well, I'd really rather just remember one law, combined gas law it is. This combines all three of those laws. You can actually forget all about those laws because all the relationships are built in right here. You have your inversely proportional relationship, you have your inversely proportional relationship for Boyle's law, P and V multiplied together. You have your Gay-Lussac relationship, P over T, and you have your Charles relationship, V over T. You have all three relationships right here. The only thing you're missing is Avogadro's law. So that's all you need here. If it turns out that you don't have, this is good for when all three variables are changing, but even if only two variables change and one of them stays the same, that's okay. For example, let's say you want to use the combined gas law, but temperature doesn't change. Or you're not given the temperature. Either way, but you know it doesn't change. Okay, well, P1 V1 over T1 equals P2 V2 over, well, if temperature doesn't change, that implies that T2 and T1 are equal. If they're equal, then I can simply put T1 here, and guess what happens? As always, when you have the same variable on both sides, it cancels out. What are you left with? Oh, what do you know? You're back to Boyle's law. You didn't need to remember Boyle's law. All you needed was to cancel out the T's on both sides, and you're back to solving Boyle's law. And this works with any other variable as well. If, for example, you keep the volumes the same, then V1 equals V2, and they cancel out. Whichever variable stays the same cancels out, and you're left with one of the simple gas laws, the named gas laws. Let's do an example, though. Okay, so you're at the beach, you purchase a shiny red balloon. Some kind of insane clown sells you a balloon, and you narrowly escape his jaws. It's a warm day, and the temperature is 29 degrees Celsius. The balloon is large, about 8 gallons, pretty big balloon. Unfortunately, you're distracted by an aggressive pelican, as happens, and then you let go of your balloon. It floats high into the sky where the external air pressure is only 0.93 atmospheres instead of the usual 1 atmosphere. How do we know it's 1 atmosphere? At the beach implies sea level. And at sea level, pressure is always 1 atmosphere, or you can assume it's always exactly 1 atmosphere. So when you go high in the sky or high up in altitude, pressure drops, air pressure drops. That's why planes need to be pressurized inside. Too much pressure, they'll explode. And the temperature is 13 Celsius. Of course, it usually gets cooler the higher up you go, up to a point. What is the volume of your lost balloon in gallons? Now, it's okay. We started with gallons, so there's no unit conversion for the volume. Now, I just want to mention something. Note that the internal pressure of a balloon will always expand or contract, or I should say the volume of the balloon will always expand or contract to match internal pressure with external pressure. In space, balloons may expand until they pop to match the near zero external pressure. Just think of it this way. Inside of a balloon, you have little gas particles banging against the inside of the inside surface area of the balloon. But you also have external air pressure keeping that just exactly equaling out the pressure from inside the balloon so that the balloon doesn't change volume. But if you reduce the outside air pressure, if I remove some of this pressure, guess what? This balloon is going to expand bigger and bigger and bigger with less air pressure. The pressure inside is going to push out because there isn't going to be an equal opposite pressure around the balloon pushing in. So it's like pushing against somebody or pushing against a door that someone suddenly opens. Next thing you know, you're pushing forward against nothing and you fall inside, you fall inward. Okay, so that's the idea here. So this is a lot of information and there's a lot of numbers spread out here and there. The best thing you can do is make yourself a little table to keep track of all this information. So I'm going to read through this again. Sometimes I read a problem 3-4 times. So shiny red balloon at the beach. Beach implies P1 equals 1 atmosphere, automatically. You are at 1 atmosphere, 14.7 PSI, 760 torr, 101.325 kilopascals, whatever. You are at the equivalent of 1 atmosphere, whatever it may be. Temperature is 29 degrees, but of course we know we need to add that to 273 to get Kelvin. So that's going to be 302 kelvins. Volume is 8 gallons. I'm not going to bother with the decimals here. I just want to get this done. I need the space to solve. Pressure 2. So what's our final pressure? Oh, our pressure 2 is 0.93 atmospheres. So pressure in the upper atmosphere has gone down. Therefore, the pressure outside has gone down. Therefore, the pressure inside the balloon has gone down, implying that the volume, if pressure went down, volume is inversely related to pressure, implying the volume went up. However, the temperature has also gone down, which means the volume might go down. So we really don't know what the final volume is going to be. The pressure says the volume should go up. The temperature says the volume should go down. You have two different, you have two contradictory variable changes here. So temperature is, where is it? 13 plus 273. That's going to be 286 kelvins. So temperature goes down. So implying that volume should also go down outweighs the other. Did the factor in the pressure decrease, is that bigger than the factor of the temperature decrease? We don't know. We're going to have to work this out. Unfortunately, when it comes to these kinds of problems where all three variables are changing, you really can't predict. You just have to plug in the numbers to see which one wins, which factor wins, the pressure factor or the temperature factor. Which one has the ultimate effect? And this is V2. This is T2. I'm mislabeling these. Okay, so V2 is our unknown. We have to figure out what our final volume is going to be. It could go up or down. We don't know. Okay, so we use the combined gas law. We have three variables changing, therefore we better have a formula that accounts for three variables. So we have P1 V1 over T1. We're solving for V2, so I'm going to put V2 on this side. We know that P2 times V2 divided by T. I'll write it out, but then I'm going to take it away. P2 V2 over T2. Whoops, I keep writing 1. Okay, so we want to move the P2 and the T2 to the other side. So we're going to move the P2 over here. We're going to move the T2 over here. Remember, we cross multiply, cross divide. So the T2 comes up, the T2 goes up, the P2 goes down. You always move diagonally across an equal sign. Or you can just say, well, I'm going to divide both sides by P2. I'm going to multiply both sides by T2. Either way, either way. All right, so we have that. So we plug, and of course, because I did that, these cancel out, and I have P2 all by itself on the left side, which is what I want. So I'm just solving for P2 here. So I plug in my numbers, P1, 1 atmosphere. V1 is 8 gallons, not grams, gallons. T2 is 286 kelvins. Then I divide by T1, which is 302 kelvins. I'm going to line them up so that I can see my units canceling. It's always nice to be able to see that. And my P2 is 0.93 atmospheres. So you can see the units that are canceling. That always helps. So we can see that atmosphere cancels with atmosphere, Kelvin cancels with Kelvin. The only unit that's not going to cancel are gallons. Huh? Oh, I'm not solving for P2. I'm solving for V2. What am I saying here? Sorry about that. All the math is correct. I mislabeled. V2. V2. We were solving for V2, not P2. V2. Okay, same math though. I divide, cross multiply, cross divide P and T. I get those on the other side. So I'm looking for volume. Luckily, my final unit that doesn't cancel is a volume unit, gallons. Good. That tells me I'm on the right track. So I multiply and divide as needed. I take my 1, multiply by 8, that's 8. I'm not going to bother typing that in my calculator. 8 times 286 divided by 0.93, and then divide again. Divide 302, and I get 8.15 gallons. So I started at 8 gallons, so the balloon grew to 8.15 gallons. What that means is that the loss of pressure outweighed the loss or the reduction in temperature. The pressure factor overwhelmed the temperature factor. The reduction in temperature should have shrank the balloon. But because the pressure also dropped, that caused an increase, an expansion of the balloon, and that expansion outweighed. So what happened is the temperature drop, I don't know, here, stop drawing it like that. Temperature drop. Let me just color code this for you. Temperature went down, so the balloon would shrink. But pressure also went down even more. And remember, a reduction in pressure means an increase in volume. So that caused the balloon to expand even more than the shrinking effect of the temperature. So pressure factor outweighed the temperature factor. That's what we're saying. So we can see it went from 8 gallons to 8.15. That's the way we know. Otherwise, look how close it was. I mean, 0.15 of a gallon is all it changed. So it was a pretty close call. It was almost a tie. They almost canceled each other out. Now, if you see the pressure increasing by 100-fold and the temperature only increasing a few degrees, then you know the pressure effect is going to be the bigger effect, or vice versa. If you see the temperature increasing by, 5-fold, 5 times, but the pressure barely decreases or increases, I should say, you know that the temperature effect is going to be the bigger one. But in this case, they're both pretty close. I mean, 1 to 0.9, 286 to 302, both of these fractions are very close to 1. All right, let's see. Another simple gas law problem. This time again, just like all of them, I'm going to use one where we have ratios rather than actual numbers. So the gas inside of a piston is initially at room temperature. Remember, room temperature means temperature 1 is 25 degrees Celsius or 298 Kelvin, 273 plus 25. And standard pressure, remember standard pressure is 1 atmosphere. What must the final temperature be? Okay, so T2 is what we're trying to figure out because it's asking what. If we knew, it would say it is, but it's saying what. Inside of a piston, what must the final temperature inside a piston be in order to maintain the same pressure when the piston is pulled out to quadruple its initial volume? Okay. So there's a lot going on here. Pressure 2 is what then? In order to maintain the same pressure. So what does that imply about P2? P2 equals P1. We don't even care what the pressure is anymore. We could just forget about it because P2 equals P1. How about the volume? We don't know what volume 1 is, but we do know this, that volume 2 is 4 times volume 1. So we don't know what volume 1 is, but we do know that V2 is 4V1. So let's write out our combined gas law, putting all of this together. We have P1 times V1 over T1 equals, now it's the other side that we have to think about, P2 equals P1. So that's going to be, I'm going to write P1 on the other side because P2 equals P1. I'm just going to put P1. V2 is the same thing as 4 times V1. And then T2 is what I'm trying to figure out. So I'll just write T2 here. In fact, here, let me highlight it. T2. Okay, let's start canceling like terms. So we have P1 on both sides, so I'm just going to eliminate that. Once I've eliminated that, what am I left with? V over T, V over T. Hey, what do you know? I've got Charles's law. So even though it appeared that there were 3 different variables in this problem because all 3 were mentioned, it mentioned pressure, it turns out that pressure didn't change. So really, if you're keeping pressure unchanged and moles aren't mentioned, then what you essentially have is a Charles law situation where only volume and temperature are changing. Moreover, I have V1 on both sides. I have 4 times V1 on one side and V1, or 1 times V1 on the other. So what do you know? I can eliminate that as well. V1 goes away. Now the 4, of course, doesn't go away. It's still there. So let's, after simplifying all of this, let's rewrite it. So I have 1 over, remember, I eliminated both of these variables. So that gives me a 1 on the top of this fraction. 1, it doesn't make T the top. It's not T1. Does not equal T1. That is a big mistake. Just because you eliminate everything on the top of a fraction doesn't suddenly elevate the bottom of the fraction, the denominator, into the numerator spot. That's not how math works. So be careful about that. Oh, wrong color. Let me use this. So 1 over T1 equals 4. The only thing left, the variables are gone. The only thing left on top of this is 4 over T2. Now, once again, be very, very careful. Do not solve for T2 simply by moving the 4 over. If you do that, you're going to be solving for 1 over T2. Don't solve for the reciprocal. Solve for the actual number. Move the T2 up. Move the T2 up there so you have T2 over T1 equals 4. And then move the T1 across. Remember, you can only move diagonally across an equal sign. Keep that in mind. Otherwise, you're going to make a lot of unnecessary mistakes. So that's going to equal 4 times T1 T2 equals 4 times T1, and that equals, well, we already know for T1, 4 times 298 kelvins is going to equal, what is it, 1192 kelvins, if I'm not mistaken. Let me just double check that number, just in case. 1192, good, all right. Since the question didn't ask for a specific unit of temperature, I'm just gonna leave it in kelvins. So 1192 kelvins, that's our final answer. So the piston is pulled out. What that means is you've expanded your volume. Volume expansion. A bigger volume implies a higher temperature. If you're pulling out the piston, you're giving it a bigger volume. The only way pressure won't drop is if the gas heats up. Otherwise, the pressure would drop. But since we're keeping the pressure the same, the only way to maintain the same pressure is to speed up those gas particles so they bounce around just as hard and just as fast, maintaining the same number of gas particles, maintaining the same pressure, have to move faster, which means they have to be hotter. That's the reason you have to increase the temperature. So volume expanded by 4, temperature expanded by 4. And ultimately, that's what it is. In fact, you could have read through this problem and forgotten about all this math and just said, oh, 4 times the volume, pressure's not changing. That's Charles's law, 4 times the temperature. And you would have been absolutely right. Just multiply the absolute temperature by 4. Don't multiply 25 times 4. You might think you can say, okay, well, 4 times 25 equals 100, and then I'll just fix that by adding 273. No, you'll get 373. It just doesn't work that way. 373 is not the same as 1192. It does not work. Don't think you can fix the conversion between Celsius and Kelvin after the fact. No, you must convert before you put the temperatures in the formula. It just won't work any other way. Okay, so that's another simple gas law problem with barely any number. In fact, the only number in here is the 4 times. It's not even an official or absolute number. It's just a relative ratio. Well, that was the simple gas laws, or the named gas laws. The next video will cover just some other concepts related to partial pressure. We will look at some more formulas related to partial pressure, the so-called Dalton's law of partial pressure, and some other concepts related to gases, but it'll be more conceptual for the most part. So I hope you watch the video. I hope all of this made sense, and I hope it was informative. Let me know how it's going, and if you have any questions or comments or concerns, and of course, if you had any mistakes, please let me know. I'll see you in the next video. Take care, everyone.